Hi everyone, so we're going to continue look at homogeneous equations such as linear dependent and linear independent. Okay, so a set of function f1, f2, fx and fn is likely to be linearly dependent on an interval I if there exists constant c1, c2, cn not all 0, such that c1 f1x plus c2 f2x plus cn fnx equals to 0 for every x in the interval. If the set of function is not likely dependent, so if it's not likely dependent, we say it linearly independent. Okay, there are some properties. So if you want to say a function is linearly dependent if there exists a constant c1 and c2 that are both 0, that are not both 0, such that for x every interval. So for example, we have c1 fx plus c2 fx equals to 0. Okay, one function is simply a constant multiple of another function. If we can write it in this form, then we say linearly dependent. And at least one of the constant, namely c1 equals to minus 1, is not 0. Okay, one of the constant is not 0, and at least one function can be expressed as a linear combination of the remaining function. Okay, by saying that, you can say a function is linearly independent, okay, the opposite of linearly dependent, if neither function is a constant multiple of the another function, or there is no function is a linear combination of the other function. Okay, these are the two definitions of linear dependence and linear independent. Let's look at example on how to understand this. Okay, given a two function, we have two functions, f1 sine 2x and f2 sine x cos x. Determine if they are linearly dependent or linearly independent. Okay, so you have f1 equals to sine 2x. Okay, I want to change the font size here. Okay, so what is sine 2x? Sine 2x is 2 sine x cos x. Okay, so we have 2 sine x cos x, which is 2 times what is sine x cos x? f2. So this is one example where we can say that f1 equals to 2 times f2x, because the definition for linearly dependent, at least one function can be expressed as a linear combination of the remaining function, or one function is simply a constant multiple of the other function. Okay, so we say that this is therefore linearly dependent. Okay, maybe we have another example. Determine if given function, we have 1, 2, 3, 4. 4 functions are linearly dependent or linearly independent. Okay, so we have f1 equals to cos squared x, f1 equals to cos squared x, and then we have f2 equals to sine squared f, and we have f3 equals to secant squared x, and f4x equals to tangent squared x. Okay, how can I show that they are linearly dependent? Okay, so first try to write this as a linear combination of the function. So linear combination is c1 f1x plus c2 f2x plus c3 f3x plus c4 f4x equals to 0. Okay, so putting into the f1, f2, f3, f4 function, we have c1 cos squared x plus c2 sine squared x plus c3 secant squared x plus c4 tangent squared x equals to 0. Okay, so we can simplify this by plotting c1 equals to c2 equals to c3 c4 equals to 1 negative 1 c2 c1 equals to c2 equals to c4 negative 1, or vice versa. Let me just okay, how to do this? So we can write this as c1. If this is 1 cos squared, okay, let's say this is 1, so we have cos squared x plus sine squared x. This is minus 1, and c3 equals to minus 1 minus secant squared x plus tangent squared x equals to 0. Now this is 1 minus secant squared x plus tangent squared x equals to 0. So what we have here, if you can look at it, so we can have a function. Can we get a function equals to 0 here? Okay, so what we can write here, I can write a 1 plus tangent square x equals to secant square x. Okay, or I can say this one is equals to 0. So we can see that we can write this, so we have them as linearly dependent. Okay, they are linearly dependent. You can write them in this form, the linear combination. Okay, you can write it as a linear combination. If you look at the definition, see, at least one function can be expressed as a linear combination of the remaining function. Okay, so moving on to this. Now you have to do this exercise. You determine whether the given function is linearly dependent or linearly independent. Okay, I'll put it here as your homework. Don't forget to submit your homework. Okay, now another thing before time's out, I want to look at Wronskian. Okay, for the solution of differential equation, we are primarily interested in linearly dependent function. Okay, now how can we say it's linearly independent? Another way is when you have the Wronskian. Wronskian is you have given a function here, whatever function, and the second row is the derivative, and then another derivative, and then you take the determinant of that function. Prime denotes the derivative is called the Wronskian of the function. Okay, so for instance, let's look at this example here. Okay, so if y1, y2, yn be n solution of homogeneous linear n-order differential equation, then the set of solution is linearly independent if the Wronskian not equals to 0. Okay, when you have the Wronskian not equals to 0, we say the solution is linearly independent. Okay, so what we have here, let's find the Wronskian for this function. So this function, is it linearly dependent or linearly independent? That's the question. Okay, so we have the Wronskian y1, y2 equals to determinant for y1 exponent negative x, and this is exponent x. So the derivative for this one is negative exponent negative x, and derivative for this one is exponent x. Now take the determinant, this, to multiply minus this. So exponent negative x exponent x minus negative exponent negative x exponent x. So we have e to the power 0, 1 plus 1. So we have 2, which is not equals to 0. So when it's not equals to 0, we say that is linearly independent. Okay, that's the definition. So you say linearly independent when the Wronskian is not equals to 0. Okay, let's look at one more example. Find the Wronskian of this function. Okay, you have y1, y2 given as, the first column is my y1, the second column is my cos. Okay, sine x, derivative of sine x gives cos x, and derivatives of cos x give negative sine x plus pi over 2. Okay, taking the determinant, this times this, sine x multiplied with negative sine x plus pi over 2 minus cos x multiplied by cos x plus pi over 2. Okay, so what do we get? We get 0. So we say this is linearly dependent. Okay, since the Wronskian gives 0. Okay, so that's all for today on linearly dependent and linearly independent. So we want to look at more into fundamental set of solutions. So how to solve homogeneous second order differential equation. Okay, we want to look at on our next video. So first thing we want to look at is we want to make sure that y1, y2, yn, okay, we want to make sure the fundamental set of solution for c equals to y equals to c1 y1x plus c2 y2x plus cn ynx. Okay, these are the general solution, and the y1, y2, yn are n linearly independent solution. Okay, so we want to write the solution in this form. This is a fundamental set of solution. Okay, so we can, if we have this, then we can say the solution exists. Okay, there exists a fundamental set of solution, and then we can solve it. Okay, that's all. I'll look into the next slide on how to find the general solution for homogeneous second order differential equation. Okay, that's all for now. Stay tuned for my next video. Thank you.